Okay, let's get started. Plenty to cover today. I just wanted to talk to you about some famous neural net architectures. One of them is a so-called AlexNet, named after Alex Krizhevsky, who worked on this a few years ago. And back in 2012, this was the thing that sort of blew up the field in a sense, or reinvigorated the field, because this network got really good performance on some image classification tasks. As you can see, the next competitor was not even close. People tend to draw these types of diagrams of conv-net architectures. They're equivalent to what we talked about last time. These 3D cubes are basically showing all of the filters in a 3D visualization. So if you have 30 filters, each 7 by 7, that would be like a 30 by 7 by 7 cube of numbers, which is why people draw these kinds of cubes in the diagrams. So AlexNet used a whole bunch of things that we talked about, namely stochastic gradient, ReLUs, all this other fancy stuff, and also ran it on GPUs, which is something I want to talk about today. So one thing we haven't done so far is actually looked at the filters. So remember with PCA, we ran PCA on the digits, and then we said, well, the rows of W are the latent factors of the PCs are themselves vectors in the original space, which was images, so we can look at those things and say, oh, these were the principal components. Or for the faces, we have the bright face principal component, the lighting principal component. So we can do the same thing with conv-nets. The filters are, however big they are, 7 by 7 or whatever, they are things that we can actually look at. And people like to look at their filters when they run conv-nets. And here's some visualizations of what these filters look like, probably in the first convolutional layer. If there's more than one, I don't remember. But what you can see here, and what makes people really happy about these types of pictures, is that you see things that kind of look like edge detectors. So remember, we talked about edge detectors. We had the ones and zeros in the convolution lecture, the horizontal ones, the vertical ones. Someone asked, I don't remember who, what about rotated edges? So those are filters that look like rotated edges. And for those of you who've looked into neuroscience a little bit, these things kind of look like the Gabor filters. These kind of look like the filters that our brain uses to detect edges and that kind of stuff. So that made people very happy, because we like to say these neural networks are biologically inspired. And it's kind of nice, I have to admit, when you see these things come out, and they're just learned, right? Conv-nets are learning the filters. You're not pre-specifying them, but apparently these are the best filters, at least assuming you found a global minimum of the objective function. You probably didn't. But these are the filters that are best for this big supervised learning task, of which these filters are only the first step. So that's pretty cool to be able to learn that automatically. Any questions or comments on this? OK, I'm going a little fast because I'm kind of squishing 2 lectures into one today because of the holiday. So I'll just keep going. I put a bunch of stuff into the bonus slides for exactly that reason. You can check them out. But basically, I just wanted to flash up on the screen that there's a bunch of, I guess, famous architectures or famous types of these neural networks that I mentioned the ImageNet challenge and that data set before. So every year or two, there's this new thing that does really well on the ImageNet competition. That's probably ending now, but they have kind of funny names. Like, so this Google Net was by Google, and it's a pun from this LeNet was famous architecture from a long time ago. So what the point is here is that over time, people are developing more and more tricks, and we're often adding more and more layers than people previously thought would make sense. And I'm not saying the ultimate thing is 10,000 layers, but there's definitely been a lot of achievements in making these things better. So ResNet, I don't know if you remember last time, I loaded up some pre-trained neural network, and we ran it on the picture of my office, among other things. And that was this ResNet, which was from a couple of years ago. So this is just to say these things exist. You can read more about them in the bonus slides. You can read the original papers. And you can also often access them by just grabbing pre-trained networks from various software packages and just using them. So, question, are we done? Did we solve everything? Definitely not. But first, some optimistic things to say. This is kind of unprecedented performance on a lot of these tasks like computer vision and speech, and that's why people are so excited about deep learning. And things are still improving. It doesn't necessarily seem to be the case that we've now plateaued in 2018. I think things are still moving very fast. And there is this general concern in some fields, like computer vision, for example, that's been a concern for a long time, is the whole field overfitting to certain data sets? Because if you remember from the beginning of the course, we talked about optimization bias. If you keep using the same test set over and over again, that could mess things up. And if a whole field of hundreds of researchers are all using the same data set for the whole field of research, there have been some interesting papers. There was one in computer vision a few years ago saying, I just took a whole bunch of research that got published and tried it on some other data sets and didn't seem to work very well. So these benchmark data sets tend to really push the field forward because it's hard to get ridiculously many labeled images. So if someone did that, that's really useful. And it also creates this sort of spirit of competition. But we have to be a little careful to make sure that we didn't just advance the field of ImageNet as opposed to advancing the field of computer vision, which is really what we're trying to do. ConvNets are making their way into all sorts of products, so I wouldn't be surprised if we're already using some of these things. So point of this is the time delay from the research paper, like say that AlexNet paper in 2012, to the time where this is happening on your phone isn't actually that long. It's a couple of years, a few years, and it's then rolled out to millions and millions of people. So that's kind of nice and impressive to see. And it makes sense because there's a competitive environment. So that's what happened. Another thing I wanted to talk about a little bit was this issue of AI safety. So sometimes AI safety isn't taken very seriously. People say, oh, Space Odyssey 2001, killer robots will get upset and mess around with us and decide to kill us or whatever. There's more to it than that, right? And I think this is a very nice example, which is that someone took one of these ConvNets that was doing a good job at object recognition, and they said, let me try to engineer a change to the image that is imperceptible to the eye by just changing the pixel intensities a little bit and try to get it to predict something else. So here's the original image. It predicts panda. Then you add a tiny, tiny bit of this noise. Here's the new image. To me, it looks exactly the same as the new image. And now it's 99% confident that it's a gibbon. So that is worrying, right? I mean, it's worrying because it makes you lose trust in the model. And I think this is a little maybe over-the-top hypothetical. But one blog post about this was saying, OK, now someone comes and repaints a stop sign, and it still looks exactly like a stop sign to you, but the self-driving car is 99% sure it's a green light or it's nothing or whatever, and then bam, right? So the point of this is to say AI safety isn't just about robots becoming conscious and killing us. It's, to me, I think a lot about the combination of systems that we don't really understand with malicious humans that want to leverage that and engineer that in ways that are actually destructive. And this is an example of that happening. Any questions or comments? Okay.
What's an explanation for why this is happening?
What's an explanation for why this is happening? So the way I think about it, I don't know how valid it is, but there's a lot of pixels in an image. So if this is a 100 by 100 image, that's a 10,000 dimensional space, or if it's bigger, that's a bigger space. So there's just so many directions you could go in. There's so many possible choices for the imperceptible noise to add, that if you're not just searching randomly, they weren't just randomly adding noise, they were optimizing the noise to mess with the network. And there's just so many directions you could go in that maybe you could find such a thing, right? If you just add random imperceptible noise, this is not going to happen. Still, this is weird, right? And something's not right, and the network is not robust to invariances that are really obvious to us, and maybe we need more training data, but we can't expect to have this as a training example and labeled Panda. That's too much to ask, right? But we somehow need to encourage more invariances or more smoothness in our algorithm. And by smoothness, I mean we don't want small changes to the input to completely mess up the output. And that's something we touched on a little bit even with linear regression and this whole idea of the instability of inverting the X transpose X matrix and collinearity and all that kind of stuff. Okay, so something that's covered in 540 that we don't cover in this course is, well, what if the output is itself an image? So we've talked about the output being a single number. That's regression. We've talked about the output being k numbers. That's what all this was, classification. You have a softmax at the end. You output k numbers, which are the k probabilities, one for each class. But you can also try to predict something at each pixel using these kinds of networks and do all kinds of interesting stuff with that. So for example, image segmentation is the idea of cutting the image into the different pieces. And so we want each pixel to have a label saying which piece is a part of. And I think we talked about this briefly at some point. So I'm not going to say anything more about this other than we can do these kinds of things and adapt the architectures that we've talked about to output different kinds of data structures. And it's pretty challenging to come up with good loss functions for these type of problems, but it's something that people are working on. Another nice example of this is depth estimation. So given an image, can you estimate the depth, meaning how far away is each point from the camera? So again, that's a kind of, you need a label for every pixel, which is the depth away from the camera. And there's all kinds of technologies like LiDAR that are sensors specifically meant to measure these kinds of things. But it's interesting to be able to do that just from an image and get to here. It's pretty impressive. So here's another example of work on this kind of stuff. So taking old black and white photos and colorizing them. So figuring out what color would this be. And it's not that the algorithm just takes in that image and immediately colors it. The point is that it has a training set to learn from, and it learns what kind of grayscale patterns tend to be what color in the training set, and then you can apply these to old images, and the results are really beautiful. So this is nice work as well. So, Matthew.
Does it change anything when your output is in a higher dimension space? Because for classification, you're classifying into like one of 1,000 categories, and you have many more pixels than that. But colorization is like a 3 times factor in the dimension space going up.
That's right. So both the question was, does it change anything when the output size is different than with classification? And yes, it is. And yes, you're right. With this colorization, you're right. It's the same as what I was saying for segmentation and the depth estimation, all these things, which is that you have one output for each pixel. So the key is you need to come up with some kind of loss function that is going to make sense. And maybe, in this case, I don't know the details of this work, but maybe you can have a loss function that's just for each pixel, and you can just sum it over all the pixels, and that'll be good enough. But for segmentation, for example, it's a little more complicated. You can't just have a separate loss function for each pixel because you want contiguous regions. It doesn't make sense if you have a thing of a horse and then some pixel of some other label right in the middle. So you have to think carefully about what kind of loss functions make sense, meaning what do I consider good and what do I consider not good. And that comes from both the training data and some prior assumptions you might have, like continuous objects and that kind of stuff. So if you can figure out a loss function, then roughly speaking, you can do all the things we've talked about because you can compute gradients and do optimization and all that kind of stuff. Okay, so continuing with the realm of interesting looking artistic type stuff, there's this idea of inceptionism, which is instead of learning the weights with gradient descent, let's actually learn the original image. And I think that's also what they did with the Panda AI safety thing that I showed, which is optimize the image to have a certain property. So coming back to this idea, what you could do is say, well, I'm going to fix the label. I want to get something that is going to be predicted as a banana. I already have trained the weights of the network on some data set. And then I'm going to start with some image. I'm going to optimize the image so that it's the most banana-like image I can find. So I want the probability of banana to be as high as possible for this image. And then, as I was mentioning before with the segmentation, maybe you want to add some kind of extra constraints or regularizers to help with some assumptions that you might have about how things look in the world. And you get these pretty interesting looking pictures. So this is the original noise, and this is the most banana-like image that you can get out of it with these extra regularizers. So there's a whole bunch of these. Right, so show me what you think a banana looks like is essentially the question you're asking the trained network. And you get all these very interesting looking images, and they're not, that doesn't look like something you would encounter, or at least something I would encounter, but it's very interesting. And there's recent work as well on actually generating realistic looking images. For example, there's this whole field of generative adversarial networks that we're not getting into in this course, but people are working on this thing of can we understand what makes something a reasonable image, because that really is a big step towards solving computer vision. So I think these are pretty fun to look at. And this dumbbell one in particular is great because it's revealing something about what the network learned, right? Which is that most of the images in the training set that contain a dumbbell also contain an arm. So it's interesting, right? So if you say, give me the image that looks most like a dumbbell, you get these weird looking things with arms. So another thing you can do is instead of trying to match the label, you can try to match the Z values, which means what are those hidden representations, those hidden activations at some particular layer. So I put in some image, the original image, I forward propagate it through the network, and then I can see what were all those Zs along the way, and I say, I don't know, layer 5, this is what I had there. Can I try to match that at layer 5? And can I do this gradient descent trick? And what's interesting about this is you can sort of see what it means to agree at different levels of the hierarchy. So what does it mean to have the same first layer activations? What does it mean to have the same third layer activations? And all this kind of stuff. So this is sort of a lower level match to the image. And here's a deeper layer where this matching was done. And again, you get all kinds of crazy looking images. These captions are not produced by the algorithm, right? This is after the fact, someone naming all of these creations, but you get some very interesting, both fun, but also in some cases not just fun, but also insight into what the network is thinking, which is an important step towards progress and towards tackling some of these safety policy type issues that we talked about. So if you're interested in learning more about this, I posted an article on the webpage that really delves into the interpretation of CNNs and everything that's going on inside there. So there's also this deep dream idea, and someone I think posted about this on Piazza as well, where again you're trying to match the features of something, and you get these very surreal, interesting looking images, which are pretty fun to look at. Another CNN art type thing that's been floating around lately that's really interesting is this idea of artistic style transfer. So the goal here is you have some content image, like for example this European looking scene, and you have a style image, so famous painting in this case, and the question is, can I produce an image that is showing me the content of this, but like as if it was painted by this person, or that kind of thing, or in the style of this image. And again, because I'm jamming 2 lectures into one here, I put some of the details about how this works into the bonus slides, but I'll just show you the results, which are punchline. You get these really elegant results, which I think is a lot of fun. So here's 3 different style images for that same content image, and you can jam these 2 things together using the knowledge that these CNNs have learned. Again, learned on some other training set, not just those 2 images. You're leveraging a network that was trained on some big training set to build up its knowledge, and then you're trying to match one image in one way and the other image in the other way and merge them together. Yes.
Can you go the other way, like from a painting to like a photo?
You should be able to. The question was, can you go the other way? So can you have a photo as the style image and a painting as the content image? It's hard for me to visualize what that would look like, but of course you could do it. I don't know exactly what would come out. But you should be able to. I mean, the style image is sort of this more low level, like the textures, and the content image is kind of the structures in the image, and what their feature vectors are getting matched at various layers based on certain criteria. Yeah, you could do that. I don't know how good it would look, but I think there are websites where you can either download code to do this or even just upload images and you can play around with it. So I put some links on the webpage as well. So this is another fun one. The person in the style of a pizza. I don't know if you can see the original person there on the right, but at this point this is just for fun, but I think it is pretty fun. And here's some more as well. So style and content, and then, well, I guess this sort of answers your question, Sherry, in the sense that here we have both directions of the same thing. So we have the style of the photo, and then here we have the content of the photo and the style of the pencil drawing. Yeah, so it goes on and on. Interesting stuff coming out. Some new cars in the style of old cars. It's pretty impressive that these kinds of things are coming out of just a giant trained network and these images. So the last thing I want to show you for this first part of the lecture is some work that was actually done by a UBC student who was TA for me, Ricky, last year when I taught the course. So he was working on style transfer with videos as well. You can check it out on GitHub, but there's an original video of scrolling through Vancouver, and then there are these style images, and you get these really nice videos. here's the other one. So I think the challenge here, a lot of it is computational, that you're now running this relatively slow algorithm on lots and lots of frames of images. And not only that, but you don't want to independently do the style transfer on each frame because, again, we have some assumptions about continuity between the frames. As far as I remember, his work was vastly speeding up these kinds of things. Okay, so that is part 1. Oops. Let's go to part 2. Okay, so the other thing I wanted to talk about today was software that is out there if you want to go and play around with deep learning. And I showed you a glimpse of that last time, but I want to go into it a little more today. So, every time. Okay. Right. The point of this slide is to say that there's a lot of software out there. A lot of it is very recent, meaning it is a very, very active field right now that people are working on these software packages. I mean, TensorFlow is kind of old news by now, but I remember when it came out, or the first version of it came out when I was teaching this course, like not that long ago, or maybe another course. But anyways, I guess 2015 was probably the earlier release, but the 1.0 was maybe a year ago. So these things are happening right now, and the existence of these kinds of things makes our lives a lot easier. So let me scroll down a little bit. Why do they make our lives easier? So one thing they do is they take gradients for you, so you don't need to take gradients. You specify your model architecture and just say, optimize this thing, and then you don't need to take the gradients. And they also compile the code for you to run on a GPU. So I think I've said this before, but GPUs are graphics processing units, and they're originally developed for computer graphics, rendering, that kind of stuff, but they've been sort of repurposed for general purpose computation, and especially this kind of matrix multiplication heavy deep learning stuff. So even not that long ago, say 2010, when I was working on the previously mentioned Amoeba project, I was writing stuff in CUDA to do this simulation, and it was pretty hard and pretty messy, and I was, this many threads and whatever to make it parallel. And now I don't need to do that kind of stuff anymore, or even as of several years ago, there's so many levels built on top by now that I just write it in these very beautiful high-level languages. Here's my neural net, and then it compiles it down to CUDA code for me and gets it ready to run and optimizes it on GPUs. Sorry, I forgot to say, CUDA is the language that you use when programming NVIDIA GPUs specifically. So having these things is really makes all this stuff so much more accessible, and it's not even just for, I don't know, messing around and that, when I really want to do this, then I gotta not do, write my own thing from scratch. That's not really true. So, for example, there was a talk about TensorFlow by one of the people involved in making it at UBC a year or two ago, and he was saying the whole point of TensorFlow was that at Google they used to have their research stuff and their production stuff, and they wanted a unified software framework that was good for both. And so in production, they're also using TensorFlow. So the same types of things that you can use are actually used all the way into products. Fed.
So you said that they can calculate gradients for us and stuff. We still have to come up with the loss function though, right?
You have to come up with the loss function, but often there will be some that just make sense, like classification, softmax, regression, squared error, something. I mean, if you're doing more complicated stuff, then yes. But often you can use out-of-the-box loss functions, and then you really don't need to do anything. And I'll show you that in a minute. Okay. Right, oh yeah, so the other thing I wanted to say is Python is very big in this space. So a lot of the, I guess I would say it's kind of the main language of deep learning. And it's, none of these things are native Python, but Python is kind of the host where you do your pretty looking stuff and then the real work is done behind the scenes for you to compile the code. Because Python's too slow, you wouldn't want to run any of this in pure Python. I mean, even if you do matrix multiplication in Python like you've been doing in this class, that's all calling some Fortran library or whatever. So Python is kind of the control panel, I guess, that you decide what to do, and then it all kind of happens in faster languages. Okay, so I think I got a bit ahead of myself with the GPU thing. So I've already talked about some of this. NVIDIA is a company down in California that makes these GPUs and was all about graphics and video games and stuff, and is now really jumping on this deep learning bandwagon. And their share price has gone completely insane. So I just checked it this morning. I checked today and 2 years ago, and it went up almost tenfold. So, I mean, maybe Bitcoin, but there's not that many things you could have bought 2 years ago that would have done like this. So, unfortunately for me, my wife used to work for them, and she had some shares which we sold probably before 35 even, but that's okay. So I noticed that Jeff Bezos, in his letter to shareholders, this is like the whole Amazon, everything Amazon's doing. He has this letter to shareholders every year. He specifically talked about their deep learning, and they have cloud computing and special compute instances for deep learning. So this is on the radar of the highest level of executives at Amazon. I mean, certainly Jensen, the CEO of NVIDIA, is all about this. So it's making waves, I guess, is what I'm trying to say. Without wanting to get you guys too hyped up, I think it's useful to know what's been going on out there. Any questions about this? So I'm going to show you some demos, and the point is that the take-home message is when you run stuff on GPUs, they run a lot faster. And that has to do with this parallelism of GPUs, and that they're really fast for, as I was saying, stuff like matrix multiplication. Probably none or very few of you are here today with laptops with CUDA-capable GPUs, maybe a handful. Well, these things are pretty big, I can show you. Big and expensive. So here it is. It's not going to fit in my MacBook Air for sure. It's like about this big, and $1,500. So if you're a student, you might not want to be dropping $1,500 on one of these things, right? And what's really nice is that cloud computing makes all this stuff pretty accessible. Which is really nice, especially because if you bought one of them, you're not going to be using it 100% of the time. But in a cloud computing environment, you use it for 5 minutes, and then you're done, and then they rent it out to someone else right afterwards. So the utilization of the GPUs is a lot higher than if you bought one just to play around with it here and there, and that creates efficiency. So it seems to me the big players in this are Amazon AWS. They have their service EC2, Google Cloud, and Microsoft Azure. There was actually a Microsoft event last night. I saw some of you there, so that's great. And they're all competing really fiercely to give away the most free cloud computing to get all you guys hooked and make whatever companies you end up working at use their platform. So feel free to take advantage of that. I'll use the Google Cloud today for my demo if we have time. Okay, so this is keras. Keras is one of the software packages I mentioned above. It's not really like all the other ones. It's just more like a wrapper around TensorFlow or Theano. As I mentioned, TensorFlow was built with these two views in mind, research and production, but for it to be production capable, they therefore couldn't optimize ease of use as much as if they just only wanted to optimize ease of use. So keras just kind of wraps around and allows you to use fewer lines of code to do the same thing. So you should all be able to run this if you have the notebook open, but you don't have to, of course. So I'm just downloading the MNIST data set of handwritten digits. And first I can run this with scikit-learn. So gotta get rid of this. So we saw this scikit-learn neural net before, and I can run it. It'll take, I don't know, maybe a minute. But this is kind of the more limiting basic software package. Scikit-learn is not a deep learning package. It's a general machine learning package. Interestingly, this MLP classifier was written and contributed to scikit-learn by a current UVC graduate student, which is kind of cool. He was also a TA for the course last year. Okay, so you wait 30 seconds. You get 97-point-something% accuracy. That's fine. With keras, the code looks a little bit different because each layer is its own line of Python code. So they could have had just one giant line of Python code with all the different hyperparameters, but it just become too disorganized. So the way you should think of this is I'm creating a model. I'm adding the first layer. Dense means fully connected as opposed to convolutional. And then I get to say all the hyperparameters. And you could have a whole bunch of hyperparameters, and they could be different for every layer, which is the kind of thing scikit-learn doesn't allow you to do. So you shouldn't, there's not really any code running when I run those first 4 lines. It's more just like you're specifying the hyperparameters using multiple lines of Python code, because that's the way they designed it to be more organized. And then this compile step is something scikit-learn didn't have, and this is where it decides, oh, I'm going to use this hardware and super optimize it and get it all ready to go. And that's really where the magic happens with TensorFlow or whatever you're using. And notice, for example, here I have to tell it the size of my images coming in, and with scikit-learn I didn't. Because here it's pre-compiling stuff, it needs to know how big the inputs are, whereas with scikit-learn it says, oh, I'll just figure that out when I get the inputs. Okay, so I can train the thing. And so there's some more hyperparameters here when I'm calling fit. So number of epochs, I think we talked about that. It's number of full passes through the data set with stochastic gradient. Batch size, we talked about that with stochastic gradient. So 128 training examples at a time with these little batches. And I guess that's about it for what we're looking at. And if I remember correctly, this is going to perform pretty similar to scikit-learn, both in speed and accuracy. And then we can also define a convolutional net. And I, again, had some examples for you guys before. But again, it's multiple lines of Python code just to set the thing up, because that just looks more organized that way. That's really all there is to it. So here we're looking at a convolutional layer, pooling, dropout, and then that's it, immediately flatten and just one more regular layer. So to go back to the question earlier from, I think, Fed, if I know I'm doing classification, I have 10 different digits for the handwritten digits data, I just say, well, that's the funny name for what we call the softmax law. Softmax law, so I just say, do this. That's it, right? There's no gradients or anything. So this is kind of, compile, and then fit. So this is the most, not quite the most, but a very, very high level thing where 99% of stuff that's happening is abstracted away from me, and I only say some really high-level decisions like these hyperparameters. I guess the only thing more high-level than this that I can think of is some kind of point-and-click GUI where I drag stuff in, and they do offer those on the cloud computing services. But we're most of the way there to as high level as possible because most stuff is happening for us. So yeah, maybe this takes a little bit longer. I didn't necessarily optimize this architecture to be that good, nor is this that hard of a machine learning problem, but we can just let it run. So for my third demo, I'm going to use the Google Cloud. We'll see if I can do it in 9 minutes. So I'm just going to go here. I guess I'll do this. I guess I'll do this. Okay. Just going to find the lecture. There we go. Okay. Oh, I don't know how to zoom in. Nor do I have time to figure it out. Oh, there we go. Okay. Okay, so this is the exact same lecture. I just dragged and dropped the Python notebook file. But this Jupyter notebook is now running on some machine somewhere out there. So everything I do, it's not running on my laptop. I'm just looking at it on my laptop. But I can still do stuff. And when I do stuff, that computation took place wherever their data center is. So that's okay. It was a little slow. It's just the first time. It'll be faster next time. There you go. Okay. So this is amazing. I mean, I barely had to do anything, and now this is running somewhere else. So whenever I do something, it sends what I wanted to do. It runs Python over there, figures it out, and sends it back to me. So another thing this means is that if you don't want to install TensorFlow and all that stuff, you don't even have to install TensorFlow on your machine because this isn't your machine. This is some machine that Google has already installed TensorFlow on, and so you can just do stuff. And so what I need to do here is change runtime type and pick GPU. And so they have this promotion. I don't know how long it'll last, but anyone, anywhere can get 12 hours free of GPU time doing what I just did. So I used to do this lecture with Amazon, but this was just too good to resist. So I guess it's working. But OK, now supposedly I should be running on a GPU. So I can just go and run. How about we'll just run all? And here's the other thing about keras and TensorFlow, which is so nice, is I don't have to tell it even where to look for my GPU. It's so nicely packaged up with a bow that it says, oh, let me go check for you, Mike, and see if there's a GPU. And if there is, I'll use it. And if there isn't, I'll use the CPU. And you don't even have to flip a switch telling me that you want me to use the GPU. It's just so nice and streamlined. Maybe you guys just expect that level of service. I don't know. But to me, this is very impressive. Anyway, so we can let the thing run. And in the meantime, I'll go back to the clone, which is here on my laptop. And this finished. So I guess the accuracy wasn't really that impressive. It was pretty much the same because I didn't optimize the hyperparameters or anything like that. But because it was a convnet and there was more stuff to be done, on my laptop, it took 1 minute and 3 seconds to do 1 epoch of stochastic gradient descent on these handwritten digits. I uploaded the exact same notebook. The keras, again, it's nice and put together so that if I use one of these built-in data sets, it checks, do you already have the data set downloaded? If not, automatically downloads it, so you don't even have to worry about that. If you're going to work on your own problem, you'd have to get your data up there, which isn't too hard. You can just wget or whatever from the terminal on there. But let's see what happened here. 12 seconds, right. So that's very good. That means we went from 1 minute running on my laptop to 12 seconds here, which is about a 5 times speed up. What did I write? I guess I wrote 10 times, I think. But Yeah, so on the order of 10 times is what you can kind of expect. In this case, it was 5 times good enough. So that's really important, right? And as you're running bigger and bigger experiments, faster means you can do more hyperparameter search, more epochs of optimization, bigger models, more data, all this kind of stuff. So it's not just I save myself 48 seconds or whatever. It's that usually I'm doing something, I have a certain amount of patience or time to do it, and I can do more if everything runs faster. So this is very nice, and just my point is very accessible. You don't even need to install anything. You just go on there and do stuff and access a GPU, and it's only 12 hours of free. I don't know how much it costs when you have to pay, but on Amazon it costs around, I think, $1 an hour for the regular instances, and then there's something called spot instances on Amazon that is maybe 30 cents an hour for a decent GPU, so still okay. Any questions?
About this or in general?
I don't know.
Okay, I have
The customer is always right. You tell me.
So when my parents taught me how to read, they didn't show me,
You're really taking this seriously, okay.
they didn't show me thousands of pictures of like ones. What is it that we're doing different then?
When my parents taught me to read, they didn't show me thousands of pictures of ones. Yeah, so I think humans, and I have a daughter now who's 2.5, so I'm kind of watching this happen. But I think humans, no, I mean watching her learn, right? It's interesting. I think humans probably do a lot of unsupervised learning. Like she just lives her life and figures stuff out. And it doesn't need that many labeled examples like me saying, yeah, this is a tree, and then this is a slightly shifted tree, right? So I think this is all supervised learning, right? And I think a lot of where the field needs to go is towards more unsupervised learning and towards this ability to transfer from one task to another. I mean, that panda gibbon thing shows you how brittle this really is. So there's a lot of people who are saying, oh, deep learning is the best thing ever. And then there's a lot of people saying, hey, wait a minute, like this is amazing, yes, but not even close to human intelligence. And that's kind of an ongoing debate and a very interesting thing to think about. Yeah. Any other questions? I encourage you all to go play around with these cloud services, and I hope I demonstrated that it's not that scary to get on there and start using them. Okay, so pretty short summary today. You can do a lot of cool stuff with convolutional neural networks. We looked at all the depth estimation and style transfer and all those things. They're amazing, but there's also a long way to go. And cloud computing makes all this stuff a lot more accessible than otherwise would be in terms of hardware, in terms of software, reproducibility, all these kinds of things. So it's definitely an important direction that the field is going in. So that's it for today. I will see you on Friday for the last lecture.